Sounds good. All right, so today we're going to talk through some digital workflows for restoring dental implants. So 10,000 foot view here. We're going to go through scanning. And then we'll go through some designing and some design principles using 3Shape, specifically for making tie base solutions. And then we'll talk a little bit about the manufacturing. So my wife and I, we have two little boys. The oldest one is almost 3, and then we just had a new baby. He's about a month and a half old right now. So I made this whole presentation from my phone. So hopefully it turns out all right. There we all are together. And then these are just a few of the doctors I work with at the Minneapolis VA. They're very close friends. They're some of my mentors, and there's a couple that aren't pictured in there, but they make going into work every day enjoyable. So do the patients in the dentistry, but definitely they are a big motivation for going in. So happy to have them. And we'll start out with some disclosures here. So I do practice at the Minneapolis VA. Nothing I say or present here is to be intended or is intended to be reflective or endorsed by the VA. And then I'm not paid or have any ownership in the companies and products I'll show today. I am using a demo license for 3Shape dental system. We'll go over that in part 2. And that was supplied by 3Shape, but 3D BioCAD is a company that helped me coordinate that. So like Eric said, we met when I was a dental student. So I went to the University of Minnesota from 2015 to 2019. Right afterwards, I went and did a general practice residency at the VA in Minneapolis. About midway through my residency, one of my mentors there, he gave me a good piece of advice, and he said, "Josh, pick something and be an expert at that." And at the time, we had a Trios 3 scanner in the clinic, and that thing was almost attached to my hip. I was using it for treatment planning, discussing with some of the other faculty there. It was easier to show them cases on the computer versus pouring up a model, mounting it. And so that was very helpful. And then I also got exposure to Implant Studio, which is a virtual implant planning software for guided implant placement. Not soon after that, I had overheard that the VA was purchasing some digital dental equipment. So a couple of 3D printers, some more scanners, a couple of mills. At that point, I thought, man, I'm in the right place at the right time. I should ask for a job. And so I talked to our chief and our boss at the time, and I made up a position that was kind of a hybrid approach between a staff dentist and a digital specialist there. So I had a lot of ground to cover, though, because I only knew a tiny bit about digital dentistry at that time. I know more now, but still not even close to as much as I'd like. And so I used that time after he had given me the position and I accepted it to hit the ground running and start learning. And that was during the COVID shutdown. And so there was a plethora of online webinars and content being generated online. So there was different 3Shape training seminars being hosted. And so I learned and practiced 3Shape, and I wrote out every single digital workflow I wanted to figure out, learn, and refine. And I got to work. And so I've been there for 3 years as a staff dentist now. And I'm just starting to really figure out some of these workflows. So the one today I'll share with you is restoring single implants. But before we get started on restoring the implants, I'll just give you a broad introduction to digital dentistry, at least how I understand it. So some of the real value that we get when we use digital dentistry is that we capture a bunch of human hours that it would have taken to either design or to manufacture the end products we want. So the prosthetics, the crowns, the guides. And so that's computer assisted design and computer assisted manufacturing, right? So CAD CAM. In general, the workflow for digital dentistry can be split up into 3 separate phases. The first phase is scanning. That's with our intraoral scanners, or that can be with the CBCT. The second phase is our design phase, and that's all done on a computer, most of the time with the dental specific CAD software. And then finally, phase number 3 is we need to manufacture whatever we design digitally, excuse me. And those are our 3 phases. So what's actually happening when we're scanning? We're converting analog information to a digital format by virtually stitching together thousands of photos. And what the photos do, or the computer takes those photos and it throws them into a 3D coordinate system so that you have a 3D rendering of whatever you just scanned. And so as these images are stitched together, the software will post-process it and it'll make what's called a mesh. And a 3D mesh is what we see here. It's made up of thousands of polygons. If there's a higher quantity of polygons in a certain area, that just means it's higher detail, higher resolution. And so each one of these polygons actually has 2 faces. There's one outward facing and then one inward facing. So in the video below, the outward facing is the blue, and then the inward facing is the purple. This orientation is described as the mesh normal. And then we can save that mesh into multiple file formats. They're all 3D. The majority of files that get saved and that are most user-friendly are STL files. And what that is it's just the simplest, and it's the orientation and the relationship of all those polygons I showed you. The second is a ply or a PLY, and that's everything that an STL file is, except this time it has color associated with it. Those are the 2 main file formats. Each company, or a lot of them, have their own proprietary 3D file format. For example, 3Shape, their file format is called DCM. The benefits of some of these proprietary file formats is that you can include things like annotations and then margin lines if you've marked a margin line within or embedded within that 3D file, so they can be reused. So mesh errors, if you run into an issue, it's most likely because of a mesh error. So when you're designing or when you're trying to manufacture a 3D object, these mesh errors can really hold you up. And some of the most common ones are holes. So we see there's a hole. Flipped normals, so you have some outward facing polygons or triangles next to inward facing triangles. Bad edges, so these raggedy edges here, those won't, well, this whole thing wouldn't print. But also intersecting or overlapping triangles are problematic too. So if you're going through a design and all of a sudden the software craps out on you, most likely it's because of this. So everything we scan and everything we design becomes a mesh of polygons. You might hear our 3-year-old here. I hear him downstairs. Okay, so anyways, there are some specific dental CAD softwares. The main difference that they split between these are that some are chair side, or some of these programs are chair side, and then some are lab based. The chair side programs, typically they're more intuitive, user friendly, but they're limited in some of their possibilities, where a lab software, it has a much steeper learning curve. So something like ExoCAD or 3Shape, but endless possibilities. So once we have our 3D file designed, then it's ready to be manufactured. There are two main ways in dental we use to manufacture digital devices. One is 3D printing. And then the second is milling. And so milling is considered a subtractive process. So you're taking a puck or a block of material and you're carving it using either burrs or tools. And then 3D printing is additive manufacturing. So you're building parts layer by layer. And in order for something we design or have to be manufactured, it needs to be a closed volume, or what's known as watertight. So if you see the video on the lower left there, this isn't a closed volume. These are just scans. These won't print. These won't mill. That needs to be watertight. So if you look at the lower right, they've been converted to watertight closed volumes that can be manufactured. Let's see if I can get rid of this. Okay. So a majority of the printed materials we use in dental are photopolymers. So they're liquid resins that are cured using UV light. There are a limited number of metal parts that can be 3D printed using metal powder and a laser. And then there's a very limited use of thermoplastics. I only know of one company right now using some proprietary thermoplastics to 3D print with. And so if we break it down, there are 7 recognized categories of 3D printers. Each is an additive process, but they do fundamentally vary. The majority of 3D printing we do in dental uses a vat polymerization printer. There is a limited use of material jetting, becoming a little more popular now, and then powder bed fusion and material extrusion. And I'll go through each one of those and what they are. So vat polymerization, if you see anything on Instagram, Facebook, related to dentistry, most likely it was printed using this type of printer. So these are also known as SLA or DLP or LCD printers. And what you're doing is you're taking a bath of liquid resin and then using some light source to harden it selectively. Most of the parts you make with this are plastic type parts, although they are incorporating some ceramic fillers in them now. This is material jetting. This process gets me the most excited. Benefits of this is it's like an inkjet printer. So what you can do is you can use multiple resins simultaneously. If you go back to the vat polymerization, if you have a big bath of resin, you can only use one resin at a time, versus this material jet printer. It can use, some of them go up to 8 different resins simultaneously. And so what you can do, and what we've seen recently, is you can print monolithic objects in full color. And in the lower left, we now have FDA approved resins, or Stratasys has FDA approved resins for printing monolithic full color dentures, all with one printer. These parts are typically plastic as well. There's another printing process, material extrusion. You might have heard of it, called FDM. This is where you're using a filament of material or a spool, and then you're using a heated nozzle to melt it and layer it. So kind of like a hot glue gun. Like I said, there's only one company I know of using this type of printer, and they're using it to print flexible partials. If you were to print a dental model with this printer, it wouldn't be accurate enough, and it wouldn't have a high enough resolution for what you'd need it for. And then there's powder bed fusion. You wouldn't see this one in any dental office. These printers are huge, are expensive, and they're also kind of dangerous to run. You have to wear kind of like the powders are dangerous to inhale, so you have to wear a special suit to post-process. But these, you're taking a layer of powdered metal and you're using some sort of energy source, so either a laser or electron beam, to melt it selectively. This can be used, or it's being used right now, for partial denture frameworks. And then not sure if many people would do this, but I guess underneath the metal for a PFM crown or bridge. All right, and then so our mill materials, we have a huge variety of mill materials. The mills for dental have been around. I think the first CEREC was in the 80s, and so they've only advanced and added materials here. A lot of them, the glass ceramics, the zirconia, the hybrid ceramics, we're making crowns and bridges. And then denture milling is a thing, and then you can mill frameworks or bars, and then you can also mill in wax too. So if you're gonna want to do a wax up, you can start it out by milling it and then finish it off, or you can mill in castable wax. And these materials, they come in two main formats. One's a block, the other's a puck. The blocks typically are limited to the glass ceramics, the zirconia, the hybrid ceramics, and PMMA. And then the pucks, interestingly, you can't really find glass ceramics in a puck format, but that'll be like zirconia, acrylic, wax, titanium, chrome cobalt. The blocks are convenient when you're milling a single unit, but if you're manufacturing many units or you're a lab, it's more efficient to have a puck mill because you can fit 15 to 20 crowns in one puck. And then you also have the ability to fabricate larger restorations, so full arch prosthetics, big bridges. And if we break down the mills, there are two types of mills that are useful in dentistry. They differ in the number of axes they have. So the axes are just ways that either the tool or the workpiece, so the material, can move around to be milled. So a 4-axis mill can, let's see here. There we go. So 4-axis mill can go around 4 different axes, and then the 5-axis mill has a 5th axis it can rotate around. So typically a 4-axis mill is limited to crown and bridge, and a 5-axis mill would be able to mill most other things because it has that extra axis, so it can increase its part complexity that it can manufacture. And then the second big difference between mills is that they can either be a wet mill, and so they're using irrigant to keep the tools and the material cool, or a dry mill. And there are hybrids where they can mill either in wet or dry. At least the one that we have, it's a pain in the butt switching it over, so I've just converted it to a dry mill only. And then some materials like to be milled wet, and then some like to be milled dry. The wet materials, glass ceramics, hybrid ceramics, composites, titanium, chrome cobalt. And then the dry materials, zirconia, acrylic, and wax. All right, that's our intro to digital dentistry. Now let's break down how we would restore a single implant. So similar thing, we're going to scan, we're going to design, and we're going to manufacture. So I'll go through each separate phase here, and I'll let you know when I'm moving on to the next phase. So these are some of our required parts for the workflow. You do need a scan body, an implant analog, and then a tie base. So first we'll start off with phase 1, which is scanning. Of the chairside scanners, most do the same thing, right? You're getting a 3D file, scanning intraorally. Typically, most will be able to scan for an implant there. The ones I use at the VA are Trio scanners, but this workflow can be applied to these other scanners as well. So whichever scanner you're using, it's important to remember to follow the recommended scan strategy for that manufacturer. This will help maintain the accuracy of your scans. All right, so let's talk about scan bodies. The scan body is used when making a final impression scan. Its function is the same as an analog impression post. However, it directly transfers that implant position and orientation of that internal hex to a digital format. So if we have our implant, we attach our scan body to it. We get a digital analog. And then if we 3D print a model at the end of the workflow, there's a lab analog we can use. And so what ends up happening is after you make the scan of your scan body, you're going to use a reference point on a virtual version of that scan body, and then a best fit alignment will be completed, and they'll line up the two. And so here's a video of me and the software doing a best fit alignment. So I'm placing reference points on the virtual and the scan. And then based on that, a virtual analog gets placed along with our tie base. So what we've accomplished here is the equivalent of pouring up a soft tissue model. There are two types of scan bodies available. One's an implant level, and then the other is an abutment level. So the implant level attaches directly to the implant, right? And then the abutment level, they make them attached to multi-unit abutments or the uni abutment. And then they also make scan bodies that go on top of a tie base. So what you need to do is you need to put the tie base into the implant and then put the scan body on top of the tie base there, make your scan and take everything off. There's multiple manufacturers of scan bodies. Best thing to do is to check with your laboratory, see which scan body their CAD software is compatible with, and then go from there. There are some scan body variations, so each manufacturer makes them in a different way. Some of the biggest differences are the attachment mode, the material they're made of, how they finish the surface, whether or not they're reusable, and then what softwares are they compatible with. They can get kind of funky with what softwares they decide to play nice with. So it's important to look into that before you start purchasing a scan body system. So the attachment level, they do make snap-in scan bodies, and then they make screw type scan bodies. And then of the screw type scan bodies, some can be hand tightened, and then some require a driver. Some scan bodies don't use they use a unique driver, and they don't use the same driver you would use for that restorative system. So it's important to watch out for that. Scan body reusability. Some scan bodies are sterilizable, right? Those are preferred. They do make single-use scan bodies. I actually don't know of any right now offhand. And then the material they choose to make the scan body out of, no matter whatever contacts the implant should be metal. That way, if you take a radiograph confirming the seating, you can see it. But then what they choose to use as a material above that interface differs. So what I've seen are their PEEK scan bodies, so a plastic type, and then titanium scan bodies. And one thing to consider is if you're going to be taking these scan bodies through multiple sterilization cycles, what's going to hold up long term? Probably the titanium. If you get any distortion in a scan body, say you got distortion in a PEEK scan body, it would be, you run into inaccuracies when you're going through your alignment. And then surface finish is important to consider. The surface should be matte, not shiny. Reason for that is the scanner picks up the matte finish way better than the shiny. And then CAD software compatibility. So depending on what software you're using or your lab is using, it's important to consider that the scan body would make a difference. So 3Shape, they do accept a lot of the scan bodies available, so does ExoCAD. All right, so this is the scan body I use day to day. This is a DES intraoral scan body. It's screw in. There's no screw hole on top of it, so you hand tighten it. But they do make a manual tool, and that's off to the right there that you can use to tighten it in case you have big fingers or the space is tight. They're still sterilizable. They're made of titanium through and through, and they have a matte finish. And then they're compatible with a lot of the major CAD softwares. Alternatively, if I need a custom abutment through Atlantis, I'll use the Atlantis IO Flow scan body. And this is a screw-in scan body with a screw channel. You use the same driver as the restorative system. It's sterilizable, it's made of PEEK, and it has a matte finish. And then here is a video of me placing that scan body. So these are indexed scan bodies, so they're engaging. And so you have to kind of twist them until you feel it drop into the implant. There we go. So now that we felt it drop into the implant, you can go ahead and tighten the screw, take your x-ray to confirm it's seated all the way, and then scan. And then here's that DES scan body I was showing you. So yep, you have to finger tighten it, but now they include that manual tool. So if you got fat fingers, you can still tighten it up. Nice thing about not having a screw channel through that abutment is the software. It tends to what am I looking for? The screw channel causes some issues when you're scanning. It doesn't scan into there well, and then when the scan gets post-processed, it kind of removes a little bit of the top of that scan body there. And so I do prefer not having a screw channel through the scan body. And then these are some analogs for 3D printed models. So if you're doing everything in the virtual environment, you still do need a model at the end of it. And if you didn't actually take a VPS impression and have a stone model, your only option is to 3D print it. And so these are analogs that are compatible with a 3D printed model. The model gets printed for this analog to fit inside of it perfectly. And then some of them now, they even have screws that you can stabilize the analog in the model with. All right, so I'll go through the scan workflow here, at least what works well in my hands. So first thing you're going to do is you're going to want to set up your case for scanning an implant. The reason why you do this is it's going to give you more scans that you need to make. So you're going to need 3 different scans. The first is an emergence profile scan. The second is a scan body scan. And then the third is the opposing. And so when making the emergence profile scan, that's the first one here. I like to leave the healing abutment in place, or the temporary restoration, make the entire scan, and then go ahead and trim away that healing abutment once I'm ready to scan the emergence profile. All right, and then depending on the software you're using, you're going to have different tools available. In Trios, it's the scissors icon there. So we trim out the healing abutment, take out the healing abutment, then go back immediately and scan the tissue emergence profile before it starts to collapse and change. And then you're done with your first scan. That's your emergence profile scan. So next, you're going to mark the spot where the implant is, place your scan body, and then go ahead and scan the scan body. It's important to get as much of the scan body as possible, especially at least on this desk scan body, the what is that? Almost like a triangle, 3 triangles on it. Because that's really important for the software when aligning that virtual version of it, to pick that up and accurately do that. So this is scanning the opposing, and then of course you'll scan the bite afterwards to have the case mounted, so I won't wait around for that here. So we have two main groups of abutments we can choose from for a CAD CAM screw retained or CAD CAM implant restoration. So we have our stock abutments, which are tie bases, and then we have our custom abutments, which is a milled titanium abutment. And then of those tie bases, there are some variations on the tie base available. And then, of course, our custom abutment is that titanium milled abutment there. And then we have a whole multitude of restorative solutions available using either a custom abutment or a stock abutment. We'll go through those. So a screw retained solution. And then we have our cement retained solutions. And then our screw-mentable solution. So there's kind of three main categories, right? And then here's another screw-mentable. First thing we need to decide, do we want it to be cement or screw retained? Screw retained, the only difference is it has a screw channel, or one of the big differences is it has a screw channel through the crown versus cement retained. Everything is the abutment seated separately, and then you cement it in the mouth. So screw retained is cemented outside of the mouth, and then a cement retained is inside of the mouth, and then a cement retained won't have a screw channel through the crown. And then we need to decide, do we want this to be a custom or a stock abutment? Some of the biggest differences between the two is the distribution on the ceramic that we use, or the distribution of the stress on that ceramic that we use. And then with a custom abutment, you obviously have the ability to completely customize the emergence profile. And then if we're using a stock abutment, specifically a tie base, that emergence profile is made using ceramic. So a custom abutment, it's titanium, it's high strength, it supports ceramic well, especially in cases where you have a big cantilever. And then it's potentially taller than a stock abutment. So in cases where you have a really tall crown and you need more resistance or retention, then you could use a custom abutment and make it super tall. They are difficult to manufacture in-house, so typically these are sent out to an external lab for manufacturing. And then here we can see that custom abutment emergence profile, and then it's supporting the ceramic. They do make titanium blanks available for milling a custom abutment. So the implant interface is already pre-milled. The part that you would mill in-house is the emergence profile, and then the crown part of it. And then this is a case I did for a Bicon implant. Like I said, this is tough to do. I did it for a Bicon implant because they're non-indexed implants. One of the toughest parts is milling it so that its position is correct relative to the internal index of the implant. All right, so our CAD CAM stock abutments, we'll go through these here. So this is our tie base. This is an engaging version of the tie base. And then this is a non-engaging version, an angled screw channel. And then we have a multi-unit tie base that goes on top of a multi-unit abutment. So a tie base, it's prefabricated. It's made of titanium. It was specifically made for CAD CAM solutions. It can be used for single units, or it can be used for splinted options as well. You can use them to make cement retained or screw retained restorations, and then whatever gets cemented to the tie base, it's done in the lab or extra orally. And so here's the anatomy of the tie base. We have our screw channel, the chimney. Typically the chimney is anywhere from 3 to 5 millimeters tall, just depending on the manufacturer of the tie base. There's a restorative platform, an anti-rotation feature depending on the implant system, an internal conical connection, and then an index for the restoration when you're cementing them together. So let's talk about engaging versus non-engaging tie bases. And engaging engages the internal pattern of the implants, whether that be a hex or a proprietary shape, with this anti-rotation feature. And so this anti-rotation feature acts as an index for the restoration. So it's great for single units because you know how to place it. It's only going to go in that one way or 6 different ways, right? Different brands use different shapes. And then if multiple implants are splinted using a screw retained restoration, the shape can actually hinder you from achieving a passive fit. And this is a tie base for an Astra EV, so that's the Astra EV shape. And then here are a few of the other shapes you can find, although there's lots more. And again, that shape is really important for indexing the restoration and then preventing the screw loosening if the crown was to get rotated. So then a non-engaging abutment just doesn't have that anti-rotation feature. It just has the conical connection. And that internal conical connection is where it's the zone where the abutment transfers stress to the implant. They've shown that this improves the stability of the abutment implant interface, and there shouldn't be any gap between that abutment and the implant right there. So here's a picture from Nobel. We can see here that there's no space between in the area of the internal conical connection. So when you're picking a tie base, one of the options you have is the gingival height of the tie base. So the gingival height is just how tall is that restorative platform from the platform of the implant. So we can see the different variations in the gingival height there. And then here's a tie base attached to an implant. So again, that's the platform of the implant, or the distance from the platform of the implant to the platform of the tie base. And then here's a page out of the desk catalog. There's, depending on the implant brand, different gingival heights you can choose from. So here's the Astra EV system. You can see there's a gingival height of 1 millimeter or a gingival height of 3 millimeters. So depending on the implant location and what you want for your restoration, you'll choose that. But I'll go through how to choose a gingival height here. So the ideal height of that tie base platform is just above the cresta bone. You don't want it impinging on the bone, but you want it low enough that you can develop enough of the emergence profile with the ceramic as possible. In subcrestal cases, you're going to need a taller gingival height. So if this implant was placed 2.5 millimeters, 2.5 millimeters subcrestally, I would have had to use a 3 millimeter tall gingival height. In this case, it was about 1 or a little less than 1 millimeter subcrestal. I used the 1 millimeter gingival height and got a nice result. So you can gauge what gingival height you're going to need based on the PA you have of the implant. It's also helpful to know, if you're the surgeon or if your surgeon placed it for you, how far subcrestal they placed it. So in this case here, it was placed slightly subcrestal. That's a 3.5 millimeter tall healing abutment. So I figured it's right about 1 millimeter subcrestal there. And then, so I know my gingival height needs to be for sure greater than 1 millimeter. So I chose a 1 millimeter gingival height tie base for that. There are some limitations to these tie bases. If you have a case with a large cantilever, it's going to put a lot of stress on that ceramic tie base interface and then probably break the ceramic. If you have a very tall restoration, like I was saying before, sometimes it's nice to have a custom abutment because you can have more resistance form, right? The chimney on this tie base is only 4 millimeters tall. You can have a much taller custom abutment made if you have a case where you have a very tall restoration. You do need a minimum occlusal height of 5 millimeters. And then there's no ability to completely customize the gingival height, but like I showed you, you do have some choices for the gingival height. This is a cool option. This is also from Des. This is called the Arum base. It's the angled screw channel version of the tie base. So we have our screw channel here. A big thing that they change with this is the chimney height. So it's a shorter chimney so that you can get the driver in from a different angle. But then it has a platform, an anti-rotation feature, the internal conical connection, and then the restoration index. So the way the angulated screw channel works is you have a specific or a special driver and a special screw head that are designed to be tightened at an angle. This allows for strategic angulation of your screw channel. So in an anterior case, if you don't want the screw channel going through the incisal or through the facial, but you still want a screw retained solution, you can use this to tip that screw channel to a max of 25 degrees in any direction. One drawback is that the tie base chimney is shorter, although I did watch a video of Mike Scherer at one of the conferences, and they had this tie base bonded to a zirconia crown attached to a chair, and it was the only thing holding the chair up, and you could sit in the chair and it still held. So I think you still can get a strong bond with a shorter chimney, but it is something to consider. So the concept works. We have a ball driver that allows for this special screw to be tipped 25 degrees from any angle. And then here's a case, number 10. I didn't like where the screw channel was going to be, but I wanted a screw retained solution. So I used this angulated screw channel to tip it through the lingual. So this is our decision tree for a tie base. So if you're evaluating a case, this is kind of what you want to go through. So first decide, do you want a custom abutment or are you okay using a stock abutment? If you're okay using a tie base and you're on board for that solution, first thing you're going to want to do is use an engaging abutment, right? So if it's a single unit, you want that engaging abutment for that anti-rotation feature. So it's indexed and can't rotate and loosen your screw. Next, you'll need to decide, will a cement retained solution be your go-to, or do you want it to be screw retained? If you want it to be screw retained, do you need it to be an angulated screw channel to strategically place that channel, or can you use a standard straight? Next, you'll need to choose a gingival height. So you can do that either from the surgical notes or from a PA of the implant. Estimate where that platform of the tie base is going to be just above the crest of bone. If you can't find a gingival height that's available, that puts you in an ideal relationship with that crestal bone. So if it's too low and impinges on it, or if it's going to be too high and you can't develop enough emergence profile, I would go ahead and just go back to choosing a custom abutment there. So one tie base solution we can make is a screw retained solution. We have our tie base, we have our crown with the screw channel, and then those are bonded together before we place them on the patient. And then we have a cement retained two-piece hybrid abutment. So in this workflow, we're using a tie base. We're milling a custom abutment piece. These are really nice for aesthetic cases, so cases in the anterior zone, where you want your emergence profile to be of a zirconia or a ceramic versus metal. And then those are bonded together outside of the mouth. And then that's delivered, and then you cement the crown inside of the mouth. You can also make a screw-mentable solution. It's just the cement retained crown with a screw channel through it. And then there are some tie-based solutions for bridge. You can't use not saying can't, you wouldn't get a good result with an engaging abutment. So I would recommend a non-engaging abutment, or you can use multi-unit abutments. And the reason why a non-engaging abutment works is because of this internal conical connection. So divergent implants can be restored because that internal connection has some draw to it because of that taper. So this is really critical for achieving a passive fit so that you don't have stress in the ceramic, stress on the components, or stress on the bone, which all cause problems. And so we can have these implants. So this is an Astra EV. Their internal conical connection is 11 degrees. So combined, these implants can have a total divergence of 22 degrees. It can still seat, it can still draw, so you can use a screw retained tie-based solution for that. Okay, that was phase one. That was scanning and abutment selection. So phase two, we'll move through some design principles. Just a few housekeeping things. So when you're setting up if you're the one setting up an order form in 3Shape or whatever your CAD software is, this is what you want to make sure is correct. If this isn't correct, the workflow doesn't work. And then one other thing we'll talk about are DME files. So this is an acronym for data medium exchange. These are just files made by the companies. So say DES, they make these tie bases, so they have these downloadable DME files that holds information for the materials, the implants, and the restorative components that can get installed into your program. So depending on what program you're using, you're going to want to have these installed before you design. So here I'm looking for the DES library DME for 3Shape. And you can see DES also makes them for ExoCAD, and then Dental Wings also, I think, is an option too. But then you download the zip files and then you install it into 3Shape. This is out of the scope of today's webinar. I won't go through installing those, but I just wanted to make everyone aware that you do need these DME files for that system. When designing the crown, there are some supra-gingival considerations, and these are all the things we learned back in school and afterwards. So these are the heights of contour, the embrasures, marginal ridges, incisal edge, arbuckle contour, where we want the free gingival margin to be, the occlusal relationship, those occlusal contacts, and then the interproximal contacts. And I won't go into details on those today. Subgingivally, there are different things we need to consider since this is an implant restoration. And one of the keys is we want to avoid impinging that bone with either the tie-based platform, right, or the restorative material, because that's going to cause crestal bone loss. So when you're in the design software, you can design with some tissue pressure, just depending on how much of that emergence profile you've shaped already. And what I've noticed is that anything below 0.2 millimeters, so you see here in 3Shape, let me see if it comes up here again. It'll actually tell you the value that it's penetrating that scan. So anything less than 0.2 millimeters is slight pressure on the gums. So when you're delivering, you'll get a low pressure. Anything between 0.2 and 1 millimeter, you get some tissue blanching. Things, if this value is greater than a millimeter, yeah, you may need to numb the patient up and do a releasing incision while you're delivering that restoration. And then our subgingival emergence profile. So the shape of that emergence profile is important for stable peri-implant tissue. So it can either be concave, it can be straight, or it can be convex. Ideally, it's either concave or straight. And then if we look at it in cross section, we do want it to resemble the shape of a natural tooth. So a molar, right, is that trapezoid, and then a premolar is ovoid, and then the incisor is triangular. And then Gomez Meda, Esquivel, and Blatz, they have a great paper on the aesthetic biological contour concept. So this was for implant restorations in the aesthetic zone, but what they do is they describe different zones of the emergence profile and their different functions. And so they describe 3 separate zones, and we'll go through them here. The aesthetic conditioning zone, that's blue. The biologic boundary area, that's the red. And then C is for crestal bone stability. And so those are the functions each one of these areas has. And we want that aesthetic zone, so the zone E, to be slightly convex. And that's right below the free gingival margin. In between that and the platform of the implant, we want it to be concave or straight. And then right next to the implant, where we have that zone of crestal bone stability, we want it to be straight. And then it's important we consider the angle of that emergence profile, either when you're planning implants, actually ideally when you're planning implants, and then restoring them, because we know that large emergence angles can increase the risk for peri-implantitis. And so what we're doing is we're measuring this from the long axis of the implant to the free gingival margin. And ideally, we want to keep this less than 45 degrees. We don't want it to be straight horizontal 90 degrees. Okay, that was a quick phase 2. On to phase 3, manufacturing and what to consider. What materials do we have to decide from when we're making these CAD/CAM implant solutions? So we have zirconia, we have lithium disilicate, we have 3D printed resin, and then we have titanium. Those are really the 4 great materials out there right now. When picking a material, it's important to consider how you want that material to function, right? So if you want it to be the contact point with the tie base, so you want it to have extra strength, you might consider zirconia. Or if you want it to have higher aesthetics and wears a little better than zirconia, you might consider lithium disilicate. So the fracture toughness and the flexural strength are something we should definitely consider. Ideally, I prefer zirconia a majority of the time, but if I can get enough ceramic thickness, typically it's at a molar site, I'll use Emax as well. So when we're selecting materials that go beneath the gums, it's important that we consider materials that are biocompatible with that gingiva so that we have long-term gum health. Qualities of these good subgingival implant materials include that they can get very smooth, they have a low biofilm affinity, and then we can actually get an epithelial adhesion or a hemidesmosome-like attachment to it. So materials that are highly compatible or biocompatible would be polished zirconia, polished lithium disilicate, and then titanium. The materials with low biocompatibility, so materials we want to avoid placing beneath the gums, would be porcelain, any sort of glazed ceramic, and then gold. All right, we'll go through titanium here. So titanium is typically wet milled. It has a very high flexural strength and fracture toughness, especially compared to the ceramics. It has great polishability. but it is difficult to manufacture in-house and possibly has some aesthetic issues, especially in thin biotypes or anterior areas. And I know you can get them anodized so that they're gold. That improves the aesthetics, but maybe not as much as a ceramic would. Lithium disilicate. One nice thing about this material is it's highly aesthetic and it does wear away a little bit versus zirconia. And so what the idea is that it has a little bit of stress relief, because as the adjacent natural teeth are wearing, that enamel is wearing, we don't risk, or there's a lower risk of hyperocclusion over time of that implant. So if we have something really hard like zirconia that's not wearing at all, the thought is maybe years down the road, that implant could be in hyperocclusion and cause issues. Lithium disilicate is wet milled. It does have about half of the fracture toughness and flexural strength than 3Y zirconia. So it's weaker, but also very strong. It's got great polishability. It's easy to manufacture. It has a fast crystallization cycle, so you can make the restoration fairly quickly. It does have size limitations, and then adding additional material or glaze or stain to it, you do have to run it through a furnace cycle again, so you can't bond it to the tie base, start to deliver it, realize you have an open contact, and then just easily add contact to it. You can still add the contact, but throughout the process, you're going to burn out that cement that you used to attach them together, and you'll have to re-cement them together. Zirconia, awesome material, dry milled. It's got a very high flexural strength and fracture toughness, extremely polishable. You can get a mirror shine in it. It's easy to manufacture in high detail. So if you remember, zirconia is milled in a pre-sintered state, so it's actually like 20 to 25% larger when you mill it, but you're still using the same burrs that you used to, or similar sized burrs that you would use to mill Emax, and so you're milling the same detail as that Emax, but the crown is 20% bigger, so you're getting more detail. The materials in the pre-sintered state is really soft. It's like chalk, so it's easy to add more detail if you want to. Post-processing though and sintering typically does take much more time than lithium disilicate does. You can mill very large restorations on it. But just like lithium disilicate, if you ever had to add a contact back to the materials, down the road, that contact opens up. When you put it through the furnace, you're going to burn out that cement between the material and the tie base, and you'll have to re-cement it. So green state zirconia, like I was saying, this stuff is like chalk, very fragile, very soft, easy to carve, and 20% bigger than when it gets sintered. So this is an important thing here. So if you look at a zirconia puck, there's something called a scaling factor on here. This is a number that you program into not your design software, but your manufacturing software. And what this does is it takes whatever your design is and say that's 1, and it increases to 1.21 of that size. So in this case, it would be 21.5% bigger than your design. And that way it gets milled larger, and then when you sinter it, it shrinks back down. So here's that manufacturing software I was talking about, or just an example of one program. So I'm going to add a zirconia puck to the program here. We'll give it a name, and then I'll need to enter that scaling factor so that any crown or any restoration I put in there, it automatically gets 1.215 bigger, 2151 bigger, right? And then when you sinter zirconia, you use it's a zirconia furnace, so it's high heat, like 1500 degrees Celsius over a long period of time. I think the cycle I use right now is like 9.5 or 10 hours, based on the materials instructions for use. And then it's going to shrink about 20%. Okay, good. I did have it in here. So when the process of adding a design to the material is called nesting. And so you're adding it to a virtual version of the material you're gonna mill. So you want to position that and then add sprues or attachments to it. And one thing I've learned through trial and error is to always check those sprue attachments, make sure they're not on critical areas like interproximal contacts or that emergence profile. And then here in this program, you can see, here, let's see this one. Yeah, when I double click, there's red. That's all undercut. So that's area that doesn't get milled well if the sprue is there. And so I like to move the sprue up to that height of contour so that you get a cleaner and more accurate mill. There we go. And then you calculate the tool paths, which is just another word for milling instructions for the mill. And then you mill. One important concept to understand when milling is over milling. So this limitation is unique to milling. And what it is the mill burr diameter limits the ability to mill sharp contours. So you see here the angles of my abutment are sharp. And so what the program has done is it's over milled those areas so that when the restoration is made, it'll fully seat. What ends up happening though, not in this case, in other cases, is you can get thin areas in the ceramic, or you can get a sloppier fit of the restoration on the abutment. And then lastly, the other material we can use is 3D printed resin. This resin is evolving every single month. Currently, there are multiple definitive crown resins available. So these are resins that are considered high strength and approved for permanent use. One of the arguments for these being more advantageous for an implant restoration is they're able to wear very similar to tooth. And so you reduce the long-term risk of an incidence of hyperocclusion. So if the adjacent teeth are wearing, but this isn't wearing at the same rate, eventually you'd get hyperocclusion. But since this is wearing at the same rate, you avoid that consequence. It's easily repairable. I think this is one of the biggest benefits of having a 3D printed crown, because you can just easily add, you would air braid it, prime it, place some bond, and then some composite. So if you get an open contact a few years down the road, you can take everything off, go through that sequence, add the contact back, place the restoration back in, and you don't have to put it through a furnace. So you don't burn out the cement between the tie base and the crown. And then one of the benefits of 3D printing is you can print very large restorations, and then multiple units take the same amount of time to manufacture as a single unit because everything's getting printed simultaneously versus a mill. You have to do one at a time. When you're nesting for a 3D printer, it's different. You're not using, or you're not placing the restoration within the puck of material because there is no puck. So what you're doing is you're placing it relative to the build plate of the printer, the build platform, and then adding support to it. So I'll flip these around. These are some custom healing abutments. The orientation of the part on the 3D printer will affect the resolution of the printed part, the accuracy of it, and then where those supports get added. Some considerations when staining and glazing your restoration: you want to limit the stain and glaze to everything that's supra gingival. You want to avoid placing that glaze subgingivally because it's not as biocompatible. And then you want to stain and glaze it because you have to do that in a furnace. You want to do that before you cement it to the abutment or tie base. And ceramic polishing is a great option, especially for the subgingival portion. This is polished zirconia, and you can see the very low surface energy there. That water on there just kind of balls right up. So plaque debris doesn't really adhere that well to it. And then the tissues love it. You even get like a hemidesmosome like attachment to it. So you get a very good peri-implant seal. Some very healthy gums. Ceramic polishing, they make multiple systems. This is a 3-step system. And then this is a 2-step system for zirconia. And then for that same system, they just make different shapes for it. And then this is diamond polishing paste. I love this stuff. Typically I'll polish first with the wheels, but then use the Robinson wheel with this diamond paste, and this really gives it a high shine. Okay, now that we've made our restoration, we still need to make our 3D printed model, unless you took an analog impression and have a stone model. And then we need that implant analog that pairs with the digital design of the model we have. And that analog just gets seated right in there. So when you're going through the design process, and then you 3D print the model, it just makes an attachment spot for that analog. And then you can add articulating cups. And this is a plastic ball joint articulator that you can super glue in there. And then the stilts you see are centric relation or bite relation pegs. Okay, now that we have our model and we have our crown, we're ready to bond to that tie base. So we'll go through that process here. And so these bonding steps are done outside of the mouth. Some of the core principles of bonding is we want the surface rough, we want the surface clean, and we want it primed for that material. Depending on the substrate you're bonding to, you're going to treat it differently. So zirconia versus lithium disilicate versus printed resin versus titanium, you're all going to have, or they're all going to have different treatments and primers that you're going to want to use. So the surface treatment for titanium, if it's a smooth abutment, you're going to want to aerabrate it. But if it has these retentive grooves, so you see this Atlantis custom abutment here, it has kind of the ribs along it. You actually don't want to aerabrate that at all. Those retentive grooves actually improve the bond strength versus aerabrating it. And then these desk tie bases, the one in the lower right, they've already aerabrated that for you, so you don't want to re-aerabrate it. You want to handle that with gloves too, so you don't get any of the oils from your skin on there and reduce your bond strengths. Zirconia, you're going to want to aerabrate the intaglio with 30 to 50 micron aluminum oxide. You want to do this about 10 millimeters away for about 10 seconds. And then lithium disilicate, because it has glass in it, you're not going to aerabrate it, but you're going to etch it. So you can use a 5 or a 10% hydrofluoric acid etch. I believe the IFU for Emax is to use a 5% hydrofluoric acid etch for 20 seconds and then rinse and dry. So now we've roughened the surface, we can clean the surface. So after you treat the surfaces, there's different ways to clean it. You can either put it in an ultrasonic bath for 2 minutes in alcohol or distilled water. Or if you have a steam cleaner, go ahead and steam it. Or if you have some phosphoric acid etch, you can place that on the inside, rinse and dry it. All right, let's talk about priming. So this is a ceramic primer. This is made, I think I'm saying it right, Carrare. Might not be saying that right. Anyways, the same company that makes Panavia. This is their ceramic primer. So this has 2 main components in it, MDP and silane. MDP is critical for bonding to zirconia, and then the silane is critical for bonding to silica ceramics, so like lithium disilicate. So that silane bonds to the silica within the ceramic. The MDP, that phosphate group, bonds strongly with metal oxides, so zirconium oxide. And then there's an alloy primer. So this has two main components in it, MDP and VBA TTT. That MDP is responsible for bonding to non-precious metals, and then the VBA TTT is for bonding to precious metals. So when we're bonding to the non-precious metals, that phosphoric acid group within that monomer for MDP bonds with the atoms within that metal. And then it helps the reaction also with VBA, TDT, and precious metals to improve the bond strength. And we'll skip this one. Okay. And then lastly, composite resin. This is the Panavia V5 system. I use this for day-to-day for crowns and bridges. So this is what I use also for my tie bases because it also works well for that. Ivoclar makes multi-link hybrid abutment cement, and this is specifically for cementing to tie bases and abutments. And then there's another brand, I haven't tried it, called Zirconite. I believe it's a self-adhesive resin cement, so you don't need the primers, and that would be for zirconia. Some tips I've learned through trial and error when bonding to the tie base: use a cotton pellet in the tie base screw channel. That helps with cleanup, and then you don't want to get any cement on your screw. You're going to want to place the cement directly to the tie base. You're going to want to polish the ceramic near the tie base after you're done bonding. And then you want to ensure that the analog, that lab analog, is fully seated and stable before you go through this process. And then wear gloves going through this. The oils from your fingers can reduce bond strengths. So here's our cotton pellet. And after you've seated the tie base on the model, screwed it in, seat that cotton pellet in there, and then apply the resin cement to the tie base and seat the crown. And then after you're done bonding, just polish the ceramic that's near the interface there with the tie base. And we'll move on to part number 2 here, but since Easter weekend's just around the corner, I do have a couple Easter eggs I'll include in the next section. So I'll show you how to, based on the implant restoration we design, how to also design an occlusal guard for it. And then I'll show you how to make a custom healing abutment from a virtual treatment plan. So before you've placed the implant, but you've planned the implant, how you can make a custom healing abutment for placement after you place the implant. All right, thank you.
Okay, so Josh is going to switch over to a different computer here. I'll take back over for a moment.
So part number 2 here, I'll take you through using 3Shape to design a few different tie base restorations. Let me just pull up some pictures here of what we're going to go through. So first one, we'll go through a screw retained solution using the tie base, using the engaging abutment. Lastly, we'll go through making a healing abutment using a non-engaging tie base. Let's go back to the beginning there. Okay, so this is 3Shape. This isn't a 3Shape tutorial by any means. I just want to show you how the software works. So I'm going to go ahead and make a new case. And then this is our order form. So this, if this isn't set up correctly, you'll run into a lot of issues here, but let's set up, I'm going to get rid of a couple things. Okay. So let's just name our order here. Okay, and then we're going to select the tooth number. Let's see if I can get rid of that. Nice. Okay. Tooth number, abutment, and then under the abutment, there's an option for a screw retained crown. And I already have the DME files installed. Again, that's out of the scope of this webinar, but you'd find the specific DME files for your implant system. And what that does is I downloaded the DES DME files, right? So now I have access to selecting a DES tie base. This 0.02 and then the 0.045, that's the cement space that they design into it. I prefer less cement space, so a tighter fit of the crown and tie base. So I'm going to do 0.02. Okay, now you have a laundry list of implant systems DES makes tie bases for. What I'll do here, I'm going to do Astra. So there's a Astra EV, here we go. And then my implant size. So here we have implant sizes. You see 4.2, 3.6, 4.8. NE means non-engaging, E means engaging. I want an engaging abutment for an Astra 4.8. So here we go. Okay. And then at the end of this workflow, we want models to 3D print. So I'm going to select models and we'll print those. Okay. Up here in the upper right, I noticed it switched my object type on me where I'm going to use digital impressions, right? So we have scans in this case. Okay, that's the order form. So here we have our occlusal alignment. So this is for mounting on our fake bow. I'm going to jump ahead to the next step. And this is where we're going to align our scan flag here. There we go. So I'm going to reset this just to show you what it looks like. So this is our virtual scan body. We just want to select a reference point on there. And then here is our intraoral scan. And select the same reference point, and then it'll do a best fit alignment. It'll align the two, and then it'll place a digital implant analog. And then here's our tie base that we selected. Let me get rid of that here. Look at it underneath. And then I went ahead and did this beforehand here to save a little time. But you're going to design the crown here. And so you place it in the correct position. You design all your supragingival features, right? So we want marginal ridges that are about the same height. We want heights of contour that are similar to the adjacent teeth. And then we want our contact areas to be there. So I just turned on our contact map and we can see that is a red contact there, and that's a red contact there. And again, I won't be able to go through all the nuances of 3Shape here. But I mainly just want to show you what the workflow looks like. Next is you're designing the emergence profile. Let's get rid of that. We'll put that on there. So here's our crown, right? And then here's our emergence profile. You can take these sliders or the balls and move them around. I'm going to undo that. And then one thing I want to show you here is there are these green dots here, and this changes the convexity or the concavity of the emergence. And remember, we want this emergence profile to be straight or concave, right? Okay, once you have your emergence profile set, you go on to the next step here. The next step, it wants you to finalize some of your crown design. I recommend you do all the crown design in the previous step though. The step before the emergence profile. So then we would just skip ahead and go next. And so now it joins the subgingival area, the emergence profile with the crown. Let me show you here, and I'll turn this off so you can see it. Now they're combined. You can take different tools here and smooth out some of these transition lines. And then here's our occlusion. Okay. And then one thing I talked about during the lecture was the soft tissue contact. So my little indicator here is telling me the value that I'm pushing onto the gums here or through the opposing scan. You see I'm getting a little strong here. 1.3 millimeters is probably the strongest. So we're going to get some tissue blanching or quite a bit of tissue blanching during delivery. If we didn't want that, didn't want to have to anesthetize, you can just use your remove tool and smooth that out a little bit. And my recommendation initially is not to necessarily design your own and jump into that. Learning these softwares, it does take quite a bit of time. Definitely, send most of your cases out to the lab, and then if you want to get your feet wet, try taking on at least one case to work through. To learn the workflow. Eventually you get faster at it. I think for me to design a single unit takes about maybe 15 minutes in the software if I'm working quickly. Okay, next thing, it's going to assemble everything together. So what this has done is it's added a screw channel. And then one little tip I've noticed is there's this extra drill hole radius feature here. What this does is it just changes the size of your screw channel. I like to set it to 0.1, otherwise sometimes the driver binds up or you can't remove the screw from it. So set it to 0.1, make it slightly bigger. And now we have our screw retained crown there. Let's see here. There's our tie base, crown, opposing, and adjacent teeth. Okay, so now that we have our crown designed, we need our models still. So since we set up this case for models, at least I think I did. Let me see if it goes through here. I might have to go back and modify it. Okay. Looks like I'll need to modify it. So I'm going to just make a copy of it. This is like watching somebody play a one-player video game. Okay, so where's my order modify? There we go. So on this original order, I didn't have a model added to it. So I'm just going to select a tooth, add a model, click OK. And now I can build a model for this case. Looks like it's just loading here. There it goes. All right, and if you took some time and set your occlusal plane correctly, it helps you when you're making your models here. So what the occlusal plane does is whatever base it adds to your model, it parallels this occlusal plane. So we'll see that coming up here. I'll go to the next step. Up top here. So this is going to be trimming the scan. So we have a bunch of unnecessary scan data that we don't want to 3D print. I like to make the models as small as possible. And actually lately, all I've been doing is just trimming the adjacent teeth and then the implant site and printing just that. I don't even print the opposing now because you learn to trust the software after you make so many restorations. You learn what the values are in the software and what that looks like in the mouth. And so I don't necessarily need a mounted opposing 3D printed model, because it is going to be less accurate, because if you're 3D printing, there's some inherent inaccuracies with that as well. So let's go to the trim step. So one little trick I like to do here, we want to trim away as much excess as possible. So this palette, we don't need the palette at all, especially the opposing. So we're going to get rid of all that. And it looks like it screwed up my spline here. So I'm going to clear it, and I'm just going to draw a new one. So you can either click and drag or just click. And this is right around here. I don't want a super thick model, so I'll trim away the palette. Okay, let's look at the lower. Not as bad. I'm still going to trim away some of it. They don't need all that information, even that. So what I was saying before is now I'll print my models and I'll just do this. So I'll do the molar here, including the premolar here, and then the implant site, and only print that, because I just use the model for cementing the restoration to the tie base. Okay. And it'll be okay if we lose that molar there. We'll just trim that off. And same thing here, we don't need that retromolar pad. All right. Looks good. Okay, and we'll jump to the next step. And the next step, don't have anything to do there. You can see it puts our restoration here. One cool thing that, let's see if I can hide it. I'll show you later. So what the software does is it'll remove any restoration contact on the gums. It'll remove it from the model. So when you 3D print the model, your restoration will actually seat on it because it's cut out that area instead of printing rock hard gums. Now you see it adds a space for our analog. And now you can add your articulator. I'm going to go without an articulator here. And then you can emboss the case, so you know which case you're working on. Okay, we'll go next. Okay, soft tissue. This is what we want next. So we don't want this area in the model, so we want to cut it out. There are 3D printers that you can print soft tissue like resins, so it's squishy. Let's see, why isn't it adding? Okay, we'll auto place it. There we go. So if you click on it, you can change these slicers. So you can cut the soft tissue. You see here where the program has cut away where the restoration was contacting. If we were to print the soft tissue, that'd be nice because I could seat the restoration then. But I've found the soft tissue to be very unnecessary, unhelpful. I've printed it for cases, and you just end up taking it off. So cool feature, but not really helpful with the lab steps, at least with my workflow. We'll wait for this to load. Okay, let's get rid of that soft tissue there. So one thing I didn't do, and this was on purpose to show you what it looks like. So you want to protect this analog space here. So when you're doing your soft tissue cut, there's a checkbox to check protect analog. And the reason why you want to do this is you want that analog, when you place it in there, to be the most stable. And if it cuts away some of that space, that might add to some instability for your implant analog. Okay, we're back. Lower left, protect analog. Now you'll see what it looks like here. All right, let's see what happens now. We turned that protect analog on now. Here we go. So this piece, it was hacked off before, that would have, or could have destabilized our analog. So when we're cementing that crown to the tie base, it may have some inaccuracies there. But now this is better. Good. One last thing I want to show you, and this is something kind of anybody 3D printing these models needs to dial in for their specific 3D printer and their specific resin. It's your analog to model spacing. So it's how much space, it's the equivalent to cement space. Let's see if it'll show it here. Yeah, it doesn't. So anyways, it would create a little bit of space between your analog and the model so that it would actually fully seat. So it's a cement spacer. You have to dial that in for your 3D printer and for your resin. And so it's helpful to make multiple models when you're first figuring this out. And then under interfaces here, let's see. Analog to model spacing. So here it is. Right now it's set at 0.1. I don't know if that would be good for this 3D printer. I know the 3D printer I use, which is a Stratasys, likes it at about 0.075 millimeters of space around there. Just know that this needs to be customized for your printer. Okay. So after we've designed the restoration, we've designed the model, we have our files now that we can print and mill. So if you right click the case, go to advanced, you want to generate the output. I could spend a whole day talking through 3Shape, 2 days probably, and then explore cam. Sorry, I don't have the time tonight. So here's all our files that we made. So you see there's a tissue file, there's an antagonist, there's our model that we're putting our analog in, and then there's our restoration. You just pull up the restoration here. Okay, here it is. You can see all the polygons it's made of. And then let me show you the model here. And there's our model. One other thing is, I see I printed this model as a solid. There is an option to switch it to hollow. I never print it solid. It uses way too much resin. I just am on my home computer, but you can change the settings so you can have this model hollowed out. Just know that, again, depending on your type of 3D printer, if you make it too thin, the model can warp. So just like our composites, if we put too much composite in and light cure it, we get, some polymerization shrinkage, and you'd get the same thing with a 3D printed part when you're post-processing it. So thickness does matter. Usually if you stay around 3.5, 4 millimeters thick, which is pretty thick, you shouldn't get any distortions in your model. But here you can see where we would place the analog. And let's see if I can reuse this one here. So when you're doing a custom healing abutment, here, I'll make a new one. We're going to want to use a non-engaging abutment. So we'll select abutment. Let's do a screw retained. And then we're going to do des. Yeah, I'm just going to click through these here. So now we just want a non-engaging abutment for a 4.8 millimeter implant, because that's what we're planning to place in this case. click OK. So then in your implant planning software, and sorry I don't have more time to go through that, but at the end of your implant planning, when you're making your surgical guide, you're going to get these files that are outputted. One's your surgical guide, and then one's this lower, or one's a scan with implant info. So this is your scan, right? But then it has the position of your planned implant within the scan. So we can actually use that before the implant's even placed to design a custom healing abutment. And so what we're going to do is we're going to import that scan there. We just need to go to where it's saved. Here's our virtual plan files, and then lower jaw scan with implant info. So that's one we want. So again, this is when you've planned the implant, and we're just gonna, if you had the antagonist, you can put it in there. I'm just gonna click through right now. Just make sure this saved right. And I'm just gonna click through so we can get to the next steps. There it is. Okay. So again, there was no scan body involved. I had made a virtual implant plan. And then based on that virtual implant plan, I had a file with an analog in it. So this is all before implant placement. Let's turn off our color there. Okay, we'll click through to the next step. So what you'll want to do, I'll show you just a real quick crown design. Okay, and the biggest thing is just making sure the emergence area of the crown is how you want it. So we'll pull that down, pull it in. Because that's what we're wanting to customize. We need to pull that out just a little bit. Okay, real quick. Not the prettiest crown. Okay, so this is our emergence profile. Here's our crown. I'm gonna snap it to the anatomy here. Snap it to the gingiva, snap it to the anatomy. You can use these two buttons to kind of click back and forth to get your emergence profile the way you want it. All right, pretty good. Let's move on to the next step here. And we'll move on to the next step. So this is where it combines the crown with your emergence profile. You can take a smooth tool here. You can smooth the crown up here, but you notice it's not smoothing it down here because you need to check this sculpt on protected surfaces box here. Now you can smooth out this transition line. We'll turn that off so you can see. Okay, I like that emergence profile. Let me just make sure this works here. Okay, good. So there's a plane cut tool, and you can cut the crown off of the emergence profile, but you can only do it to a certain height. And so you have to do a little bit of the contouring after you print or mill your abutment. So let's see what that looks like there. Okay. Good. And so now you can take your smooth tool. We've cut this down. You can really contour this. We're going to change our strength. And we'll just reduce some of that. You will need to leave some of this stuff above the tie base here. And that you can always trim away after you've produced it. So what I'll do is I'll cement this custom healer to the tie base. And then after it's cemented, grind down any of this bumpy area here you're gonna see. There. So there's a little hump there. I'll get rid of this. So you'd probably grind down part of that tie base there, just so you didn't have it, your healing abutment super tall. Okay, we'll go next to the assembly. This is where that screw channel gets added. This is what we'd grind down, because what we're looking for in the final is going to look something like this. So this is almost the same design, put a little more time into it, but then I ground down after cementing a little bit of that tie base that was sticking up, and then polished everything before implant placement. All right, that was Easter egg 1. I see I'm over time, like 6 minutes, but the next or the last Easter egg I'll show you should be pretty quick. So I want to show you how to make an occlusal guard before you deliver your final restoration. So I think this was the one we designed. Yeah. So there's going to be an option in here to copy and append CAD design to the preparation scan. And what this does is it takes your lower jaw scan there, and then it just attaches or glues on the crown that you designed. And so we'll click that, because when we design the occlusal guard, we want to design it with that in mind. Okay. Click OK. So now if you right click the case, and there's a way for us to go into the order here. So explore order. We can find this MB prep scan here. This is the one we want. We'll open it in 3Shape. Okay, good. So now we can see we have our lower jaw scan, and then it glued on the design we made earlier to the scan there. So I'm going to take this scan, I'm going to copy it, and then we're going to make a special folder for it. And then we'll change the name of it to lower. And then I'm also going to pull the upper scan and save that. And now I'm going to use a program, and it's a free program. It's called Medit, to design the occlusal guard. So here's Medit. I'm going to go through this pretty quick here, but I'm going to make a new case. 19. Okay, and then I want to attach or import the lower scan with our design attached to it, and then the antagonist. Okay, and then there's a DCM. So these are DCM files. If you remember, that's 3Shape's proprietary files. So in this case, I do have to convert those to STL files. So I'll click that button to do that. Okay, now what we want, there we go, is Medit splints. Okay, we want our maxilla, mandible, confirm. And then we're going to make a maxillary splint. I'm going to do auto creation here. After you've made a few of these, you figure out, or you can dial in your settings. These are the settings I like. So I like to have the outer surface very smooth. I've noticed this retention value 0.3, sometimes a little high depending on the 3D printer you use. So we'll do this as 0.2 so it's not too tight. Click confirm, and then this software is so cool. It'll make your splint automatically. The only big knock I have on it is you can't, at least right now, set an articulator on there. It'd be nice to go through the different excursive movements. But if you need a quick occlusal guard, this is one way you can do it. Let's just get rid of our opposing. Okay. So here we have our occlusal guard, and you can add a name to it, or you can go back a few steps. So say you didn't like something in the design, you can go back and completely customize that. Like where I put the name. Okay. And at the end, you would save it. Okay, let's see if we can show everything here. Okay, so we have our scans, right? And then our occlusal guard, and we made that occlusal guard with our designed restoration in mind. And so we fabricated the restoration and the occlusal guard all in the same go, and both can be delivered day of delivery. So sorry I went over time there. Things took a little longer than I thought they would in my head. We're definitely going to need to incorporate a 3-shaped course where I can go through everything in more detail, describing the different nuances of 3-shape. But I just wanted to show you what the design workflow does look like. And we'll go from there. But maybe we'll do a full day course on it. I don't know. We'll have to talk with Eric. But I'm going to stop sharing my screen. And then that is it for the presentation.
Perfect. Thank you, Josh. Really appreciate it. You made a joke about watching someone play a video game. It's kind of like watching someone beat a video game. If you weren't good at the video game, then it wouldn't be fun. But that was impressive, your knowledge on this. And thank you for sharing all the different aspects. And like you said, probably could spend a day or two on this entirely. But we've got some questions in the chat, and we'll make a copy of those. And Josh had planned to put together some responses for people. But yeah, let's do it again sometime soon. Thank you guys all for joining. CE credits coming, and then we'll send out some information with the answers to the questions. All right. Thanks, guys.
Thank you.
Thanks, Josh. Appreciate it. All right, guys.